In our last video, we took a look at the introduction to our trigonometric functions. We looked at solving right triangles and extrapolating on that idea into the real world. We looked at converting from degrees, minutes, seconds to decimal degrees, and we looked at one bearing type. And today we are going to expand a bit, because one of the things we said was that those trigonometric functions only worked for right triangles, but we know that so much of the world can be divided into triangles that are not right triangles. And yet we'll need to be able to somehow calculate the lengths of the sides and figure out what's going on. So let's get into how we might extrapolate on this idea of sine, cosine, and tangent for a 90 or right triangle with a 90-degree angle in it to a triangle that doesn't have a 90-degree angle in it. Maybe even one that's larger than a 90-degree angle. So I've got here on the screen our Cartesian coordinate system, and we'll kind of get back to our basic definition of angles. We'll start by maybe creating a line here, starting at the origin. We'll just head due east, just right along the x-axis there. And then we will duplicate that, but rotate the second one a bit. So maybe here. So now we've got these two sides, and we've rotated through some angle. We kept the side down here at the origin. We kept that pinned so we could rotate the other side. And I'm going to go ahead and put arrows on that because we know that rays continue on forever. Well, we'll call where we started our initial side. Kind of makes sense, initial being the first. And we will call where we left the second ray our terminal side. That's where our angle ends, hence terminal side. We'll call this origin, the point about which we're rotating, our vertex. So now we've rotated about the vertex, this second ray, and stopped somewhere at a terminal side. It should be noted that when we rotate counterclockwise this way, that's a positive rotation. Had we rotated the other way, maybe we end up down here. Well, now, rotated this direction, that would be a negative rotation. So our positive rotations rotate counterclockwise. Negative rotations will rotate clockwise, and we will have some negative angles that we'll have to look at. And really that just means we rotated clockwise instead of counterclockwise. But really get used to that sense that our angles are going to rotate counterclockwise when they're positive. So let's take a look now at kind of just the general outline. I've downloaded a protractor off the web, as this lets us measure angles. And we'll look at the numbers on the insides of the protractor, and we'll see, like, it starts right here at 0, and then rotates up through 10, 20, 30, all the way up here to 90 is straight up. And then it keeps increasing over here to 180. That's due west or to the left. Keeps rotating around to 270, which is straight down, and back up to 0. But notice it goes 330, 340, 350. So that would be 360 degrees. So one full circle is 360 degrees. And we'll kind of get a sense for the way that works. We'll spend a fair bit of time looking at that, those different angles. We do need to get used to where how many degrees in each quadrant. A quadrant, you'll recall, is a quarter of our coordinate system. So 90 degrees goes from horizontal to straight up or straight down. And so we'll look at that. Some of the angles we looked at before. Here we rotated a positive. It looks like 60 degrees. So this would have been a 60-degree angle. And down here, it looks like we rotated a negative. Now, if the negatives are how many degrees we've lost. So notice it's at about, looks like a 247 maybe. The 247 though is out here. So if we wanted what we rotated negative, then we would maybe subtract that 247 from 360. Go ahead and borrow one. So we've got a 3, a 1, and 1. So it looks like negative 113 degrees. We could also note that we rotated through 90 to get down here, and it was another 23 to get to the terminal side. So those are some of the calculations we'll do to measure these angles and to figure out where the angle is at. Let's take a look, kind of expand on that just a bit. And we'll talk about some coterminal angles. So if I were to right there. Oh, I jogged a little bit right at the very end. So we'll go right there. It looks like that's 130 degrees. So, oh, I don't need another line. I need my brush. Rotate through 130 degrees. Well, that's cool. Are there any other angles that end right there too? Absolutely there are. We could start at our initial side and rotate counterclockwise. Now we've rotated through 90, 180, plus another 50. So 180 and 50 is 230, so that's a negative 230. We could have also subtracted our 130 from 360. That would give us the 230. So there's right there two angles that are coterminal. Coterminal angles share a terminal side. Now notice we could have found this one, like I said, by subtracting the 130. So we could have done 360 minus 130. So that would have been positive. Maybe that's not what I want then. Maybe what I want to do is take my initial measure and subtract 360 from it. That gives me negative 230. So maybe I just subtract 360 from the angle. I'm going to denote the angle this way. That's one of the symbols we'll use for angles sometimes. So if you subtract 360 from an angle, that will give you a coterminal angle. Well, what if I don't want to go to the negative? I'll take that 130 and I'll just keep going all the way around until I get to where I needed to be. Well, I just added a full circle. So maybe I'll add 360 degrees to the angle and get another angle that ends at the same place, a coterminal angle. Well, I can do that as many times as I want. And I will find more coterminal angles. I can add and subtract 360 all day long and find angles that will end at that blue ray. Which is actually a nice way to watch movies, but gives us ways to find coterminal angles. Now let's extend on that just a bit. Back to our original angles. We already talked about how complementary angles, I'll just grab an angle here, maybe a 40-degree angle. Oh, I should get my initial side. That seems important. Okay. We talked about how complementary angles add to 90. So I'll call this maybe alpha and this one beta. Alpha plus beta equals 90 degrees. Therefore, they are complementary. Maybe I continue all the way down to here. It's not a initial side or a terminal side so much as whatever it takes to get all the way over to the 180, because back to earth or back to level ground seems like a good idea. So maybe nope, I need to leave the line. I'll call that gamma. Gamma plus alpha would be 180 degrees. We call that supplementary. When they add to 180, they're supplementary angles. And that can be really useful to us. We will take advantage of that a lot. And let me share with you why here in a bit. We're going to talk about reference angles. And reference angles will allow us to create right triangles that have the exact same sine, cosine, and tangent of a larger angle. And so being able to find an angle's complement or supplement will become really useful to us. Let's take a look at what I'm talking about here. So if I have an angle, say right there, and I'm looking at one of these days, I'll remember to switch tools. Looking at this large angle here, that looks like it's about 300. No, I'm sorry, it's 210 degrees. Just looking at the wrong number, and it didn't make sense to be over 300. So 210 degrees is the big angle. Now, notice if I were to go from this terminal dot to the x-axis, I create a right triangle. Remember to change the tool this time. Now I've got this little right triangle. I've got a little angle inside here. The size of that angle is the 210 minus the 180. So I'm subtracting this 180 portion. 210 minus 180 is 30 degrees. And now, because this is a 90-degree angle up here, I know that this is a 60-degree angle. And this looks an awful lot like that triangle I told you to memorize in the last video. It's a 30, 60, 90. Well, we know the sine, cosine, and tangent of 30, 60, and 90. And as it turns out, the sine of 30 degrees, which we already know is 1/2, equals the sine of 210 degrees, with a slight variation in that sine is negative down here in the third quadrant. And we will talk about that. Well, now, let's talk about it. We have, I'm going to come back up here to the first quadrant for a minute. Let me go ahead and hide the protractor for a second. That might be getting in the way just a bit. I'm going to drop this down here, and we'll just look at the first quadrant for a second. Okay, got a bunch of stuff in there. Well, right triangle. I needed to change tools. Right triangle. The point up here is the point XY, right? Back from algebra, which tells me the distance. This leg of the triangle is the X. This leg of the triangle is the Y. Now, we could say, this is going to feel kind of weird perhaps, but we could say, it's like a triangle. Use that. Might call that a triangle there. And if that's the case, then this would be the radius of the triangle. All right, so let's take a look at what that means for us. So looking at this right triangle over here on the right-hand side, the sine of alpha will equal opposite, which is y, over the hypotenuse, which is r. The cosine of alpha would be adjacent, which is x, over the hypotenuse, which is r, and tangent of alpha will be opposite over adjacent. Knowing this, we can see that the relationship between x, y, and r are going to help us find sine, cosine, and tangent. Now I'm going to jump down here into this triangle we made in the third quadrant, where we have negative x, we have negative y, and we have r. So the sine of 30 degrees down here is opposite, which is negative y over r. Because that's not really 30 degrees, that's 210 degrees. Only we created a little triangle down there. It was a right triangle that we could use to solve for these larger angles. This point on the end here is the end point of 210 degrees. It's also that vertex of that triangle we created down there in the third quadrant, where x is negative and y is negative. That allows us to see that the sine would be negative. So the sine of 210 actually doesn't equal the sine of 30. The sine of 210 is negative sine of 30 because we have a negative y value down there in the third quadrant. Speaking of which, first quadrant, we have positive x, positive y. Second quadrant, we have negative x values and positive y values. Third quadrant, we just proved we have negative x's and negative y's. In the fourth quadrant, we have positive x and negative y. Well, this is going to become useful for us because we just created these relationships. So if x and y are both positive in the first quadrant, then sine is positive, cosine is positive, and tangent is positive. because of this relationship in the box. Where x is negative over here in the second quadrant, that means cosine is going to be negative, tangent's negative, sine is positive. Sine uses y and r, so sine is positive. Cosine uses x and r, so that's negative. Tangent uses y and x, and when one's positive, one's negative, you get a negative. Down here in the third quadrant, y is negative, so that means sine must be negative. X is negative, so that means cosine must be negative. And tangent is 1 divided by the other. Negative divided by negative is a positive. So tangent is positive down here in the third quadrant. In the fourth quadrant, y is negative, so that must mean that sine is negative. X is positive, so cosine will be positive. Tangent is 1 divided by the other, and a positive divided by a negative, or negative divided by a positive is negative. So what is positive in these quadrants? In the first quadrant, they all are. In the second quadrant, only sine is positive. In the third quadrant, tangent is positive. And in the fourth quadrant, we found cosine to be positive. Now, you will find me often referring to the idea that all students throw chalk, because all are positive, sine is positive, tangent's positive, cosine's positive in the first, second, third, and fourth quadrants, respectively. And so I will say all students throw chalk to remind myself which of the functions is positive in which quadrant. Now, if sine is positive, then cosecant would be positive. It's simply the reciprocal. If tangent is positive, then cotangent would be positive. If cosine is positive, then secant would be positive. So those other three also follow this rule, but if I just stick with the first three, I can really delineate where these functions are positive and negative. And that's another reason that the sine of 210 down here is negative, because sine is negative in the third quadrant. All kinds of stuff. And that's a lot of information. I try to give little tips and tricks that will help you remember them, like all students throw chalk. I've also heard that all sisters trade clothes, though I don't know that that's true. All students take calculus. Heard that. I know that's not necessarily true, but whatever it takes to be able to remember where these functions are positive and where they're negative, then you'll want to stick with that. We'll be able to use that quite a bit for our work. Well, let's take a look at another problem, perhaps. I'm going to go ahead and draw in another circle. See if I can make it light. And then let's draw a line up here. Okay, so got this angle in here. You know what? I probably should have drawn that in another quadrant so we get better practice. I haven't done anything down here in the fourth quadrant. All right, so I've got my angle down here. Let's extend the vertical. Let's say that this length is actually 1 and not 5. Well, yeah, we'll call this a 1. We need the hypotenuse. So we've got a squared plus b squared equals c squared. 1 squared plus 1 squared is c squared. Come to think of it, this looks really familiar. 1, 1 root 2 Well, that was our 45, 45, 90. So now we know the size of that angle to get from the terminal side up to the x-axis, which tells me that the entire angle was actually 360 minus 45, which would be 315 degrees. So we're looking at a 315 degree angle. But we're going to look at this reference triangle, because we know that the value of that point at the end of the terminal side is the same for the 315 or the 45 in the fourth quadrant. That point is the same. And so we'll have a negative y value, we'll have a positive x value, we'll have a positive r value. All of those things are true. We know that since all students throw chalk, cosine is positive down here, sine and tangent are negative. All of those things we know because of the size of the angle, but we'll just really look at that reference triangle, which means also that this 45 degree angle is our reference angle. It is the angle created between the terminal side and the x-axis, whether that's on the right or left side of the y. It's the angle to the x-axis. That's your reference angle. And now we can find the sine, cosine, and tangent of 315. We'll use our reference triangle. Sine is opposite over hypotenuse. Opposite is -1. Hypotenuse is √2, which we could rationalize to -√2/2. Cosine of 315 degrees is adjacent over hypotenuse. We would rationalize to √2/2. And tangent of 315, opposite over adjacent. Oh, and that's a negative. All students throw chalk, only cosine was positive. And we did that by using that reference angle and the reference triangle, noting that they were coterminal. They end at the same spot. That point at the end of the radius is identical for the 315 or that -45. And we'll just take advantage of that and concentrate on that little right triangle, because we know sine, cosine, and tangent work on the right triangle. They don't work on the 315. They work on the little right triangle, but they give us the same value. So we will take full advantage of that. Let's take a look at another problem here. Might be rather useful for us. The problem says that we're given the idea that tangent of theta equals -2/3. And theta is in quadrant 2. Find the others. All right, we're in quadrant 2. Let's go ahead and draw a line out here. Quadrant 2, I don't know where it goes, but that might be close enough. Let's see, the angle theta that we're actually looking at is here. But if I drop my vertical and create a reference triangle, I could pretend it's there. All students throw chalk, all are positive, so only sine is going to be positive over here. Because I've got a -x and a positive y, r is always positive. So tangent is -2/3. Now tangent is opposite over adjacent. So the value of the opposite length is 2. The value of the adjacent length, or the magnitude, would be 3. Which one was negative? It's the x value. We need to find r, a squared plus b squared equals c squared. So r would be the square root of 13. We need the 6 trig functions. Let's go ahead and get those. Sine of theta, opposite over hypotenuse, 2 over root 13, which would be 2 root 13 over 13 if we rationalized it. Cosine of theta is adjacent over hypotenuse, negative 3 over root 13, which becomes negative 3 root 13 over 13 if we rationalize it. Tangent of theta is given, negative 2/3. Cosecant theta is simply the reciprocal of sine. So that's root 13 over 2. Notice it is also positive because we're in the second quadrant. Secant theta is simply the inverse of cosine, not the inverse, the reciprocal of cosine. So that becomes negative root 13 over 3. And cotangent of theta is the reciprocal of tangent, so negative 3/2. We found all 6 trigonometric function values for this angle. We weren't given the size of the angle, but we were given that tangent was negative 2/3 and that theta is in quadrant 2. And so we could draw a reference triangle in quadrant 2. It didn't matter that I didn't draw it to the right size. I just needed the arrangement of sides. I recognized that tangent was opposite over adjacent, so I could plug those magnitudes in. X values in the second quadrant are negative, so I made sure the negative applied to the X value, not the Y. We found the R, and then it was simply a matter of Y over R, X over R, Y over X, and so on, to get those 6 trigonometric function angles. All right. Let's add just a bit to that. And I'm going to go ahead and put in another circle here. Seem to like the circles today. They're helping me a little bit. So our circle. What if we have a quadrantal angle? Kind of an odd term. Quadrantal angle has the terminal side on an axis. So that would be like 90 degrees or 180 degrees or 270 degrees, for example. So let's pretend that our radius is 1. I know I drew it as 7, but let's pretend it's 1. So the value out here would be the point 1, 0. The value up here would be the point 0, 1. The value over here would be the point negative 1, 0. And the value down here would be the point 0, negative 1. So now we've got X values and Y values for each of those points. R we know is 1. If it's true, and I argue that it is, that sine of theta is Y over R, cosine of theta is X over R, and tangent of theta is Y over X, then we can find sine, cosine, and tangent for all of these angles. So up here at 90 degrees, sine of 90 degrees is y over r. The y is 1, r is 1, so that's 1. Cosine of 90 degrees is x over r. The x value of that point is 0. R is still 1. So the cosine of 90 degrees is 0. The tangent of 90 degrees, y over x. Y is 1. X is 0. That's undefined. And you would find that if you plugged it into your calculator. The tangent of 90 degrees it gives you an error message. Interesting. Let's take the cosine of 90 degrees. We got 0, just like we said. Sine of 90 degrees will give us 1, just like we said. And so using these points, notice we didn't really need our calculators because we recognized this point and we let our radius be 1, about 180 degrees. Sine of 180. Sine is y over r. The y value of this point at the end of the 180 is 0. Cosine of 180. X over r. Tangent of 180. Y over x. 0. We could do the same thing at 270, and 360 is just back to where we started. And any coterminal angle with those quadrantal angles would give me the same thing. And so we can really play with this a fair bit, and it gives us some good values to help us out. Let's look at, let's see, if we have some reference angles that are similar to the ones we're used to. I'll come back to this triangle, not the triangle, the circle. One of these days I'll learn my shapes. I am going to go ahead and make it the radius of 7. And I am going to send a line up here, 45 degrees. R equals 7. We talked about similar triangles. So if I drop a vertical there, or I drop a vertical here, I'll get two triangles that are similar. And I know that a 45, 45, 90 has 1, 1, root 2 as its sides. So over here where I've got 5, 5, 5 root 2, apparently my radius isn't really 7, or I'm dropping something the wrong way. But what is 5 root 2? Let's take a quick look. I'm curious what that value is. 7.07. It's really close. So because I draw great wider lines, it's close enough, perhaps. But notice that the reference angle was 45 degrees. While my entire triangle is larger, I can use this closer similar triangle and find sine, cosine, and tangent. We know that the sine of 45 degrees is root 2 over 2. We saw that earlier in our previous video. Well, if we use our larger triangle, sine is opposite over hypotenuse. I factor 5 out of the numerator and the denominator. Those can cancel. 5 divided by 5 is 1. And I end up with 1 over root 2 which would rationalize to root 2/2. So you can see that even with a bigger triangle, meaning longer length sides, as long as that angle is the same, I'll get that same value. So let's go ahead and take advantage of those reference triangles. I'll draw them again to make sure we get these memorized. We've got a 30, 60, 90, whose ratio of sides is 1, 2, √3. And we have a 45, 45, 90, whose ratio of sides is 1, 1, √2. And if we can refer to those and have those reference triangles, all of a sudden we know the coordinates here at the end of our terminal side, regardless of how big R is. So we'll take advantage of that later. And we have one more bearing type. And I will end with this. Let's pretend that this is a compass rose. And so we've got north, south, east, and west, just like we did before. Only our new bearing type is going to be a little different. I'm going to take a line and I'm going to draw it down here in the fourth quadrant. Remember before we said, well, this is south 30 degrees east. That was our first bearing type. Our new bearing type, sometimes called an azimuth, always starts on the north and rotates clockwise. So if that's south 30 degrees east, then this is also a bearing of 150 degrees. Remember that 30 degrees east would be down here, and in order to get all the way down to south would be 180. So those are supplementary angles. That's how I found the 150. So we may have a bearing where they give us a value. All they do is give us a number. Say this is 225. So you travel at an angle of 225 degrees, say 40 miles per hour, at an angle of 225, and that tells you exactly where you're going. It always starts north and rotates clockwise to where you end up. This is more often used in aerial navigation or maybe ship navigation, whereas the other one is used more often on land. And so that's our big difference. This south so many degrees east would be more on land, and travel at an angle of 150 would be in the air. If they don't give you the south, north, then you know it's this azimuth or the second bearing type. If they give you the north, south first and then east, west second, it's that one. But regardless, it gives you the direction that they'll be traveling. And that wraps up section 6.3. And so we've covered all of the material in our first week of class this semester. Hopefully this helps. Give it a look, and I hope you enjoy it. If you have questions, let me know.